replace
Sir, about the lift, when the
people you're being recorded now, so be careful about what you say.
Sir, about the normal force. I don't feel. I think physics sounds but I want to
actually
zero.
Actually, okay, let's go back to the point about the normal contact force and the thing.
Yeah.
Actually, strictly speaking, when the normal contact force becomes negative, it's no longer called normal contact force. It's actually a tension really. That means you're pulling on the flow now.
Yeah, but the thing is, because I'm standing inside the lift, then I put a rope. So
Okay.
I treat it as although I am in contact with the surface, my foot.
Yes.
Okay, there's no force.
So what happens is that when the end goes negative, what it means is that you're now pulling on the floor. But if there's nothing stopping, that means if your feet is not glued to the floor, now what happens then is that you will get separated from the floor. You go to zero, and then you start climbing up the rope. So you'll be detached from the floor.
Oh yeah.
Yes. Okay. Cool.
Yeah.
Okay. Now today I'm going to go through one very important equation, and it's going to link to a lot of other things. So you have to pay close attention, but don't be confused by all the examples I'm going to give you today. It's actually back to one formula, and that formula is F equals to dP dt. Now there are a lot of subtle ideas about this. I'm going to unpack this slowly. Yeah. So let's take a look at this. First question: when is this equation correct? When is dP dt equals to delta P upon delta T? When?
Constant change.
Constant change, that means the force is constant, yeah? The force is constant, yeah, that's correct. When the force is constant, dP dt at any point of time is actually equal to delta P upon delta T. Why? Because if the force is constant, the momentum change per unit time is constant. Which means that if I take dP dt over here, it is the same as delta P delta T. However, if I got a situation where this is the case, do you agree that dP dt is actually the gradient of this graph at that point? Whereas delta P upon delta T is actually this divided by this, which is actually the gradient of the graph P. Which is meaningless. Which is actually not meaningless, it is the average force. It is average force. Just like instantaneous velocity and average velocity. So what I'm trying to bring across to you is that there is a difference. Yeah, when we take total change in momentum over total time, you have to be aware that you're not finding force. Or we are finding force, but you have to be careful what force you're finding. You're finding average force. You're not finding the force at all points, which can change with time. Okay? So this is an idea that I want to, you must be sensitive to this idea. That this is not equal to this in most situations. It is only equal if the force is constant. Okay?
So this eliminates half.
Yeah, correct. Half part is very constant. Now, the next thing I'm going to go to is to simplify things and to just focus on this portion over here, delta P from delta T. And I'm going to surface one concept about momentum. Let's see whether you're sensitive to this. Now, if I got two balls sounds weird. 3 balls over here. I got 3 balls over here and it hits the wall. There's 5 kg, 5 kg, 5 kg, and it's at 4 meters per second, and then it bounces off at 4 meters per second from this wall. Yeah? So the question is, find the change in momentum. Second, find the average force if the ball stays in contact for 500 milliseconds.
Sorry, momentum is m.
Again, sorry?
Mass multiplied by speed.
Mass divided by velocity. Yes, right. So I'd like to find the change in momentum and the average force by the ball on the wall. Go ahead. There are 2 things that are a little bit subtle over here. Yeah, be careful. It can be 1, it can be 2, depending on you.
First question 47.
Go ahead. Find the change in momentum is a number, and find the average force by the ball on the wall. And of course, the third thing is, why is the force an average? What do you call it? Average force? Actually, quite simple. The change in momentum is just 5 times 4, 3 times 4 times minus the same number, so it's 0. So the change in momentum is 0 because it's 5 times 4 minus 5 times 4.
What's the speed doesn't change by sir, momentum is a scalar, not a vector.
Momentum is a vector.
Then there should be a change because the direction changes.
So be very careful about this. Students fall for this. Now the reason why I think it is probably more obvious to you is because 4 minus 4 is 0, then you start to think that it's impossible. Like if I give you a 4 and 2, sometimes students actually fall for it. So you need to be very careful to identify a direction that's positive, which means that this is negative. Be very careful there, right? Okay? Yeah, be very careful about it. Momentum is a vector, 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 vector. So vector subtraction, vector addition, vector subtraction, vector addition. So you must be very sensitive to it. Now with this, it becomes a numerical question, and go ahead and try it. But there's yet another booby trap. Let's see whether you can read. Say that the total change in momentum is equals to the final initial momentum, final total momentum minus initial total momentum, which is 3 times 5 times minus 4 minus 3 times 5 times 4. So which is going to be 2 times 3 times 5 times 4. That's going to be 60, 120 minus.
So define this direction as positive.
Yeah, we can define the other direction as positive. It doesn't matter. So long as it's consistent with the sign. Yeah, so long as it's consistent with the sign. And the good news about physics is that change is always final minus initial. There's never a case where change is initial minus final. It's always final minus initial. So there's a certain system in the language of physics. Yeah. Now, which means that the average force is equal to, you don't need calculator.
This thing divided by 500 milliseconds.
500 milliseconds, which is half a second. 0.5, and this is equal to 240 newtons. Now, question to ask you: does the negative sign mean anything?
Direction.
Yes, correct, exactly, direction. So the direction of force on the ball, is it the direction of force on the ball or on the wall?
Actually, should be on the ball, I think.
Is it the force on the ball or on the wall?
It's by the ball or the wall.
By the ball or the wall. Okay, let's take a look. We talked about this force causing a change in momentum. Is it the change in momentum on the ball or the wall? Ball. So is it the force on the ball or on the wall?
On the ball.
On the ball, exactly.
Yeah.
So is the force on the ball towards the left or towards the right? Left.
Direction
So it is negative, which makes sense. Yeah. The negative force is on this in this direction, therefore it makes sense. Yes.
So is it newtons per second or is it just newtons?
It's newtons because force is rate of change of momentum, which is newtons, or kg meter per second square, which is newtons.
So is that normal contact force?
Sorry?
Is that normal contact
Yes,
force?
that's normal contact force. We are assuming that there is no friction. That's only normal contact force. Yeah. Anyway, even if there's friction, if the ball is incident normally on the wall, there's no friction. Friction doesn't have effect. So, is this the answer to this question? Be careful when you say yes. Look carefully if this is.
Like ball on wall. So you eliminate the negative sign?
Yes, but before you eliminate the negative sign, you must say, to answer this question right, you must say this in the exam. Yeah? By newtons. Oh, yes, correct. You must mention this. Force by ball on wall is equal to negative force by wall on ball. Therefore, ball on wall is equal to 240 newtons. You must state this, otherwise you get problem minus. Now, this is not being difficult for you. This is not trying to be, make life difficult for you. Actually, in a sense, it is not. But the thing is that you just need to be. It is technically wrong. You just say that minus 240 is the force by the ball on the wall. It is wrong, technically. Right? Yeah? So very, very important thing. Now I'm going to throw a spanner in very soon. As you copy this down, one last question. What is the force average? Because the actual force on the wall is never going to be.
It's not the same.
It's not the same, yes, right? It's not constant. In the actual life, how do you think the force will be changing? If you got a force against time graph.
Increase and decrease.
Yes, correct. It most likely be this. Most likely. Yeah. This is when the ball is like squashed. In fact, in real life, I mean, it shouldn't be this because the 3 balls, it should be a it should be 3 pump, pump, pump. And then some students will start asking, how come the 3 balls can go through each other? It is. I don't know whether you can see this. Like the ball hits the wall can do the thing. Hypothetical balls can pass through each other.
So maybe it's angle, but then if you see it one.
Thank you for giving me this idea. Yes, I'm going to give you a question with angle. Thank you for.
Oh.
Thank you. So now there you have an angle ball. 60 degrees and 60 degrees, 4 meters per second, 5 and 4 meters per second. Yeah? And 5 kg a in contact with the wall for 500 milliseconds. How do you find the average force for this situation? How do you find the average force on the ball? Let's see how much of vector subtraction and addition you will remember. In your secondary school years, do you remember how to minus vectors? Okay, let's check. Let's do a revision. If you have vector A plus vector B, and this A, B vector being like this. Okay? So vector A plus vector B, how do you sum these two vectors?
Actually, it's draw a
parallelogram, yes, correct. So, or triangle. So you shift it such that the mantra is such that you shift the arrow such that the head of one arrow touches the tail.
Yeah.
Then the resultant is from the very tail to the very head. Cool. Now subtraction is actually not difficult. If you have A minus B, the same thing, A over here, B over here, you can actually see it as A plus of negative B. Now what does a negative B vector mean? So you reverse this, it becomes negative B plus A. The same rule, the tail of one meets the head of the other one. So this becomes your A minus B. Now why do I have to go through this with you? Because momentum is a vector, yes, correct. And why do I have to go through vector subtraction with you? Because the change in momentum is equal to final minus initial momentum. So your task now is to apply this method of subtracting vectors in this situation, where this is the final and this is the initial. Final plus negative initial. Free to ask me to explain anything.
So
Yes,
in this case, the directions of the momentum is no longer just two.
The direction
for the last scenario, there are just two directions.
Yes, correct. Forward and backward. Yeah.
But this one is more than that.
This is two-dimensional.
Yeah, the momentum you are looking for, is it this direction like
No,
final?
it's just change in momentum.
Oh, okay.
Yeah. I can give you, this is actually an easy situation because it is symmetrical. I can give you an asymmetrical situation. But the method is the same. So you take final momentum minus initial momentum. Factorially. I'll give you another 30 seconds to just form the picture in your mind. How do you subtract these two vectors? And then I'll show you how. There are two ways to find this, the difficult stylo way and the easier way. So this is equals to final plus negative initial. So you flip the initial, the final is here, and the initial is here. Therefore, the change in momentum is here. Let's throw in the angle, shall we? So 60 degrees is the final and vertical. So final and vertical, so this is 60. Therefore, this will be 60. Same thing, if you do the same for this, is 60 degrees. And it is perfectly symmetrical. So it's actually comprising of two right angle triangles. So the easier way out is change in momentum over 2 divided by final momentum or initial momentum, it doesn't matter, is equals to, this is 30 degrees.
Cosine 30.
Cosine 30 degrees. Yeah, correct. Then with this, you'll be able to find the change in momentum. Which is equals to 2 times 5 times 4 times cosine 30, which is equals to 21.
Is it same to splitting the force? Like
Splitting the force.
Same result.
It means splitting the momentum into x and y direction. Or
Yes.
Then I throw away the.
Can.
the downward force are the same.
It is okay for this because this is symmetrical and it is only, if you are sensitive enough, you know that it is only the horizontal momentum that changes. You can do that. But what if you are given a situation if they are not symmetrical?
But if not symmetrical, then
Maybe there's an energy
Then you
loss.
change the momentum either point down or point up. Right? So it's not that easy anymore. Then it will be better to
This
use
one's better.
Yeah.
But that's where we have
Second one, okay. But
I don't understand. I understand this problem. I don't understand. I thought it's PF minus PI, right?
Yes, PF minus PI. So I put it as PF plus negative PI.
So from this diagram, we just reverse
So
the arrow.
PI reversed.
Yeah, and then you bring the PF above.
And the same thing also PF plus negative PI, isn't it the same?
Yeah. Then from that, how do you get?
So this is the change in momentum, right? So this diagram that we get rid of. Yeah. Then can you see that this is actually half of the change in momentum because of the symmetry, yeah? So half of the change in momentum divided by this either final or initial momentum, which is this one, isn't it cos 30? That's how we get it. Then the answer will be simple. You just need to take change in momentum divided by the time, you get 40 root 3. 40 root 3. Okay. It looks difficult, but actually the method, I can give you something that's asymmetrical, then you just have to use cosine rule.
In that case, I think we need combination.
Yes, you need combination, definitely. But it's just more difficult mathematically, it's not difficult conceptually. The concept is still the same. Can I just do a quick scan? Any problem? Now, let me ask you a question. Can you deduce whether friction was involved?
In this case,
Was friction involved?
let's think about it.
Obviously, normal contact force comes into play, but does friction come into play?
Actually, I think no. I think
Say so? Yes, no? Yes? Yes? Guys? Your intuition. Does friction play a part?
no.
Does friction? Okay. How do we know? Do you agree that friction must act along here, either up or down? If friction acts. Yeah. Now, therefore, do you agree that if friction were to act along this direction, there must be a change in momentum in the vertical direction? Now, look at the diagram again. Is there a change in momentum in the vertical direction? No. Because this is, if you work it out, this will still be the same as this momentum. Therefore, since there's no change in momentum in the vertical direction, therefore friction doesn't come into play. Right? Because if there is friction along the plane over here, there would be a change in momentum if there's a friction.
Actually, in your theory, it's friction. That's exactly the symmetrical situation. Right?
No, it is only without friction that's why it is symmetrical. Because only
Asymmetrical.
only this one. Then it will be the asymmetrical situation.
Asymmetrical. Sorry.
It will be the asymmetrical.
Pronunciation.
And let me ask you, if you know the strike here, this is the case where it is this angle equals to this angle. If there is friction, do you think it will be A or do you think it will be B?
Oh, A lah.
Oh, yeah.
Do you think it will be A or B?
Wait.
Think carefully.
Wait.
If there is friction, okay, the dotted line over here is where the angles are the same one, which is this case.
Okay, it's B. B.
If there is friction, is it B or A? Okay, let's do a poll. How many of you say it's A? How many of you say it's B?
Unanimous.
Okay, I take it that the rest of you is either
Wait,
all of the above, all of the above, all of the above. Quantum and diagonal of the two states. Yeah, quantum and diagonal of the two states. Okay, deduce carefully. Now the thing is that if there is friction, does it reduce or increase the downwards component?
Reduce.
If it reduce, if previously it's like this and the vertical component is like this, and then now it reduces,
So
so do you agree that it
yeah.
So you assume it decreases vertical displacement.
yeah, the vertical momentum will reduce because the friction will be acting this way. Yeah.
Oh, alright.
So you can actually make this kind of deduction. It is possible. Yeah. Yeah. I like this kind of question because there's no numbers, but yet it tests your understanding. Quick scan. Any questions? Anything from beginning to now? Yes.
Joseph was asked, what do I 500 milliseconds?
Oh, okay. Okay. I only focus on the change in momentum. So in order for you to find force, eventually you have to take this divided by 500 milliseconds to find the average force.
But by the way, sir, that 500 milliseconds, I think friction plays a role.
Okay, for the case I give you over here, friction shouldn't play a role because if you check the momentum, it is the same vertically.
Yeah, but how does it pause for that half a second if there is no friction at all?
Now what happened is that basically it basically compresses this direction and then goes
Just this
vertically, horizontally.
Alright.
So if we consider from the microscopic level of friction, then here is an angle, and then there's another angle. So I feel it's like, it's not, I mean if it's horizontal, then I can understand there may not be microscopic friction, but there's an angle.
Okay, you're talking about real life situation, right?
Yeah.
Yeah, you're correct. Real life situation, it's impossible for you to have a coefficient of friction of 0 like in real life. So in real life, most of the time it will be this case. But I'm just giving you a hypothetical situation. I'm trying to make your life easier, come on.
Okay, thank you.
Yeah, I'm trying to give you a life, it's ideal condition, yeah? It's ideal condition. So you're correct. You're correct. In real life,
But if it's horizontal, then it is possible to have no friction.
if it is horizontal, what do you mean? If it is perfectly like this?
Yeah.
If it is perfectly horizontal, even if it is rough surface, it wouldn't matter.
Yeah, so there's no friction, right?
Even if there's, my point is that even if there's friction, it doesn't matter. Because there is no motion in this direction. It's just there.
So friction is only a vertical direction.
It's along the surface. Makes sense? Friction must be along the surface.
Oh,
Yeah, friction must be along the surface. How come friction causes you to jump up?
It doesn't need because right, friction is just electric attraction into object, right?
No, it is not attraction. It is not. Okay, let's go back to the fundamentals of
the
friction.
chain
Friction is because of this locking. It's actually when you try to push on it, it is this. When you try to move this, there is this side that pushes on this side backwards. So it is not because of electrostatic attractive force. It's because of the normal contact force of the surface that pushes it backwards. If you've got two surfaces that's perfectly flat, then there will be no friction no matter what's the normal contact force. That's when mu equals to 0. Even though there are atoms of it. But there's no such thing called a perfectly flat surface. There's no such thing in the world. There's no such thing. Yeah. Probably there is, but I don't think there is that we have access to.
But in this case, when the light bounces off a mirror, does it mean like it's actually because light can be treated as particle, right?
Yes, so your point being?
So actually when there is a reflection of light, the angle of incidence may
In
not
this case, perfectly symmetrical. Yeah, this angle incidence equals to angle reflection. But if there's one way you can actually find that light doesn't bounce off the obey, that will be interesting. If you can find that case.
right?
Actually, all you need to do is to find one case. Right? I mean, you learn TOK, I mean, you learn. You can say a law, but one case if you disobey. Ah, that's interesting.
It's impossible.
Is it because mirror is
Hang on, before you say it's impossible, I urge you not to say that too early. Yeah. It is not observed, that's what you're saying.
But
Yeah.
like millions of times people observe it, but it's
No, because when you
experiments of verification,
Is that you need one time?
you just need that one. Yeah. In a special case, and then you'll understand that hey, there's something incomplete about that rule. Yeah. Okay. Cool. Right. With this, probably one more thing that I will go through before I leave. So, but before I do that, any final question? 10 seconds.
last MV throw two balls that question ratio 4-3.
Okay, if not, then I'll go to the next part, which is still back on this equation. So this whole lesson, there's only one equation here. You have to really understand. Just use it a different way, yeah? Now I'm going to introduce a little bit of integral, but it's really just touch the surface kind. Yep, just touch the surface kind. No worries, I have to finish all the content first before I start throwing you this mana. Okay, very simple, just check your understanding of integral. So if I have dp dt equals to f, now do you agree that dp equals to f dt?
Yes.
Yep. So if I integral, this will become change in p equals to this.
Yeah.
Right. What does this mean? This is the something more familiar. What does this mean?
Actually, f times
dt, dt, f times dt. So what does this mean physically? Or if you are not sure,
instant,
what does this mean?
the instantaneous.
Let's go graphical. What's the graphical implication? Is the area under y-axis graph, right?
Yeah.
So yeah,
Force over time.
force over. So this means that the change in momentum is equals to the area under a force time graph. Okay. Yeah. And it also means that back to this equation, this means that F is equals to the what of the momentum time graph plot. Gradient.
Yeah.
So this is what I want to leave with you before I go. Okay? That the change in momentum is the area under the FT graph, whereas the gradient of the momentum time graph is the instantaneous force. Instantaneous force, you must represent it correctly. Instantaneous force, not just force. In fact, I will be a bit more picky. It's instantaneous net force. Yeah, instantaneous net force.
So have you done any ASP?
So I hope that you're not feeling confused now. It will come. I will make it obvious to you. I'll say this is ASP. Yeah.
So this is HL physics.
No, but hang on. There are portions where I actually go further, meaning that I ask probing questions. Yeah, like this kind of a light fiction, those kind of things. I went further. There are certain parts I went further, but technical, like really hardcore ASP stuff. I will signal to you very clearly that this ASP is okay for you to be confused.
So is it more difficult than A levels?
Yes.
For ASP content or HL?
Yes. In A levels, they don't handle. It's a rigorous program, but they don't handle integrals. Let's just click up. Ever since my time, they don't handle integrals, and most differentials. So, but I'm going to teach you integral very soon. Yeah. Once I finish the mainstream component for this term, then I'll start off the part. But you see, you must see from the perspective that ASP component brings you closer to real life. Say for example, air resistance. Come on. In what planet do you live in where there's no air resistance? Probably moon. But real life. I mean, when you fire a mortar or projectile, there is air resistance. In fact, there's Coriolis force and all those things come into play. You know, when there's spinning of the, all these things come into play.
So what is
Yeah.
like the ASP topics?
Okay. I will for kinematics and for kinematics, I won't do the ASP for uncertainty. I'll do the ASP for kinematics and dynamics. So for ASP for kinematics, I'll be doing on existence of air resistance. How do you handle air resistance using integral? Then for dynamics, I'll handle cases of for collisions, two-dimensional collisions. I'll handle situations like the pulley system where there's more pulley. Yeah, I'll handle weird pulley system. Yeah, interesting situations. Then how am I going to handle this? I'm going to handle situations where in a frame there's accelerating. Most of the cases we are handling frames that's not accelerating. Yeah.
Can you propose a solution to that question?
I'm not going to give you a solution. You give me the, you struggle through. Yeah, can? You go work it out. You go work it out.
No solution.
Oh, I will show you the solution only until I'm satisfied of the number of people who have tried it. Okay? So,
But
live with the discomfort. Live with the discomfort, yes, it was.
Yeah.
It is definitely Olympiad standard. Yes.
So if you integrate dt, don't you just get p?
Yeah, if you integrate dp, no, because if you integrate dp actually is pi to pf. So it is actually p, but you have pi to pf. So it's actually pf minus pi, which is delta p. Yeah. Okay. So there's limits on it. And then you integrate from t1 to t2.
already determined.
Okay. Yeah. It's definite integral or indefinite integral. Definite integral. Okay. Just let me